Okay, hi. I just wanted to talk through this example that is in your handout. It is a cylindrical coordinate system example. The car speed is constant going down this ramp at 1.5 meters per second. We want to find the car's acceleration. This is as a vector, so it'll have magnitude and direction. We have the tangent to the ramp at any point is at an angle phi equals inverse tangent of 12 over 2 pi r, or tan equals 10.81. Okay, now where did that come from? How do we get that? Well, if you take this ramp and you unroll one of the coils, so you just unwrap it and spread it out, we know that with each roll it goes down 12 meters with each lap. So if we make it a triangle here, we have 12 meters in one revolution of the ramp. The length of distance that that car has traveled as it comes down that one loop is the circumference, which is 2 pi r. So it comes down 12 meters in 2 pi r, or in this case the radius is 10 meters, so that's 20 pi. And we get the inverse tangent of 12 divided by 20 pi, which is what we are seeing up here. So this is just telling us that angle phi, and that will be necessary here as we move down. So our plan, we're going to use cylindrical coordinates because our problem is based in, it's got a radius and it's got an angle as it rotates down that ramp. R here is a constant, so all derivatives of R will be 0. So that's going to make our problem much easier. Our given, we have velocity of the car is traveling at 1.5 meters per second. That's the speed going down the ramp. The radius is 10 meters. It's constant. So R dot, R is not changing as a function of time, nor is it accelerating as a function of time. So R dot dot is also 0. Our equation for three-dimensional velocity in the cylindrical coordinate system, we have the velocity vector here equals r dot ur in the r direction. Well, that's 0. Then we have r theta dot in the transverse direction. Okay, we'll have that. Then we have a z velocity in the z direction. So our velocity in the radial direction, since the radius is not changing, that's just 0. Velocity in the theta direction is r theta dot, also known as r omega. It's the radius times the angular velocity in radians per second. And our velocity in the z direction is z dot, or dz dt. So as we mentioned, we don't have we need to find theta dot and theta dot dot in order to solve for acceleration. So we have, I'm going to skip down here toward the bottom, we have the acceleration equation. We have r dot dot, that's 0. We do have r, we need a theta dot, and we need a theta dot dot, another theta dot here, we need a z dot dot. So we got to find those, and then we can plug things into this equation. Now we're not given a function for v in terms of theta, but we do have some geometry to look at. So let's go back. We're going to make another triangle here. We have the velocity of the car going down the ramp is 1.5 meters per second. We did find this angle. That's the steepness of the ramp. And we know we don't have any velocity in the r direction because radius is not changing. So velocity in the z direction is going to be a component of the velocity of this hypotenuse. So we can take the 1.5 times the sine of 10.8. That's this angle here. That gives us our velocity in the z direction. Our velocity in the transverse direction, or the theta direction, is going to be our velocity here times cosine of 10.81. Now if our velocity were a function, we could still find v theta and vz by taking the cosine and sine of the components of that velocity. Okay, and it gets more complex if the velocity in the radius is changing, then we need some functions here. But in this problem, we're going to find out our v in the theta direction is this velocity times cosine of phi, and that equals our r omega. Our radius, 10 meters. Our omega dot. Omega dot equals 1.5 cosine of 10.81. So we can solve this for theta dot, 0.147 radians per second. And since the velocity is constant, our theta dot is constant. We don't need to take the derivative of a function. If we had v is changing as a function of theta, then we need to take the derivative. How about our z velocity? Our vz here, we talked about. This is our z dot. What is our z dot in this problem? Well, we know v, and z dot is going to be v sine of that phi angle. So we have 1.5 sine of 10.81, that equals z dot, it's 0.281 meters per second. Again, since our velocity is not changing, our z dot's not changing, so our acceleration is 0. So z dot dot 0, theta dot dot 0. Now we can plug these things in. So r dot dot 0, our radius is not changing. We have 10 meters. We've got 0.147 theta dot. This is the angular velocity. That's squared, and that is in the radial direction. Then we have 10 times theta dot dot, which is 0. So that's 0. We have 2 times r dot, which is 0. So that's blanked out. And we don't have acceleration in the theta direction. How about the z direction? Well, we already talked about z dot dot is 0. We also don't have acceleration in the z direction. So this comes down pretty quick. We have negative 10 meters times 0.147 squared in the radial direction. That gives us a negative 0.216 meters per second squared in the radial direction.